Hey everyone, it's Mr. Glover here. Just about to get started on our next set of notes. So we've spent a couple days on quadratic functions now. The first day we focused on graphing the functions and we basically used a table of values to graph these functions. The next couple of days were on, well, they were math labs and we only did the one. But there's two major concepts. The one major concept is that the solutions to a corresponding equation match the x-intercepts of a function. And then the math lab we did yesterday was about transforming functions. It was about moving them. So we can move them up and down, we can move them left or right, we can flip them upside down, and we can also stretch the functions. So that's the idea today, is we're going to build on this idea of transforming functions, but we're going to be doing it by hand mainly instead of using graphing technology the entire time. So we'll start out with just defining a parabola. So a parabola is a curved graph based upon the function y equals x squared. This is the most simplistic quadratic function. So to graph it, as we've done before, we're going to pick some x and y values. -2, -1, 0, 1, and 2 are a good starting point. We're going to plug them into our equation. So -2 squared gives us a y value of 4. -1 squared gives us a y value of 1. 0 squared is 0. 1 squared is 1, and 2 squared is 4. So now we've got what we need to plot this function. It's -2 and 4, -1 and 1, 0 and 0, 1 and 1, and 2 and 4. And so the parabola takes a shape that looks like this. Parabolas can be translated vertically by adding or subtracting, a constant. So for example, y equals x squared plus 2. Well, this is going to move it 2 units up, as we saw yesterday. This x squared minus 7 is going to shift our function 7 units down. And so we can tack a number on at the end after x squared, and that will effectively move the function up, down, or down by as many spaces as we want. The vertex of this particular parabola here is 0, 0. The domain of this particular parabola here is that x can be anything. Remember, domain is like asking what x's are allowed, and you could put any number in this without breaking rules, so x is all real numbers. The range, though, is restricted because, as you can see, it's strictly greater than 0 or equal to 0. So y is greater than or equal to 0. The axis of symmetry is the line that matches up with your vertex. So it's the y-axis in this case. It's the line x equals 0. And then the maximum or minimum value. And this is going to do with whether the function is oriented upright or upside down. In this case, we have a minimum value, which tells me that the minimum is y equals 0. Parabolas can be translated horizontally by changing x into x plus or minus a constant. And a is a constant. So for example, we've got the function y equals x plus 2. We're going to use a table of values here, but I'm going to show you that you don't need one every time, especially for the simpler functions. We'll pick the same values, -2, -1, 0, 1, and 2. And we'll figure out how these are going to relate to points on our graph. So if we plugged -2 into our function, we'll go through some sample calculations here. This is going to be y equals -2 plus 2 squared, which is 0 squared, or 0. This would be y equals -1 plus 2, squared, which is like 1 squared or 1. X is 0 gets us the y value of 0 plus 2 squared, which is 4. And this gets us the point y equals 1 plus 2, which is 3 squared, or 9. And again, y equals 2 plus 2 squared, which is 4 squared, or 16. So if we plot this, minus 2 and 0, minus 1 and 1, 0 and 4, 1 and 9, I think we're starting to get the picture here. But the problem is that we've only got half our function. You might think that this is the whole thing, but we would need to go further to the left. So we can, this is not ideal, but we can add more on the bottom. We can go minus 3 and minus 4, for example. Probably should have put them at the start, but that's fine. If we plug minus 3 in, y equals negative 3 plus 2 squared. Well, that's going to be like minus 1 squared, which is 1. If we put minus 4 in, y equals, negative 4 plus 2 squared. That's like 2 squared, or 4. So the same thing happens on the left-hand side. We go minus 3 and 1, minus 4 and 4. And our function looks like this. Now, the next graph we do, I'm not going to use a table of values. There's one there, but we have an easier way of doing this. I want to focus on the pattern that we're finding with all of these basic parabolas. So we're starting out at the origin, and the origin might be at 0, but it might be somewhere else if we've moved it. But counting from the origin outwards, if we move one space over and one space up, we get to our next point. And that's because we moved one space and we moved up 1 squared, which is 1. Same with the left, over 1, up 1. If we move 2 spaces over, then we're going to go up 2 squared, which is 1, 2, 3, 4 spots. Same thing on the other side. So it's over 1, up 1, over 2, up 4. If we move over 3, we're going to move up 3 squared, which is 9. So basically, as long as there's not a stretch being applied to your parabola, as soon as you figure out where the vertex is, you can just graph it by going over 1, up 1, over 2, up 4, and that's usually enough. You don't really need to have all these extra points. This is how I graph most parabolas. If there's a stretch, sometimes a table of values is required. But if there's not, this is much, much simpler. So for example, in this case, I'm going to scrap this. I've got the equation y equals x minus 3 squared. So this is going to be a horizontal translation. My minus 3 tells me that we're going to translate it 3 units to the right. All right. Now I know with a regular parabola, I always start at 0. So if I'm moving 3 to the right and that's it, I'm going 1, 2, 3, this is my new vertex. I can go over 1, up 1, and then over 2, up 4, and I have graphed my parabola. That's a little bit easier, but you have to have an understanding of what this does in order to do it this way. If you don't know that this moves at 3 to the right, then you're probably not going to be able to graph the function this way, and you're stuck with the table of values. But if you know how the transformations affect the graph, you can graph things much faster. If you don't like this technique and you want to just stick with tables of values, go ahead. But keep in mind, it's going to take you more time because you have to fill out the entire table for the whole function. Notice the direction of the translation is the opposite of what you might expect. And that means if it's x minus 3, we're moving 3 to the right. If it's x plus 2, we're moving 2 to the left, and so on. All right, so graph the following. So these ones are very similar. However, we don't necessarily only have horizontal translations now. We can move up and down as well. So the first one, adding a 3 at the end, what that's going to do is it's going to shift it up 3 spots. It's going to move up 3 units. So if we want to go and graph this, origin would have started at 0, but we're going to move 1, 2, 3 up. Okay. There's no stretch because there's nothing attached to x squared. So over 1 up 1, over 2 up 4. And we're done. This one's a little bit trickier because there's two translations happening. There's this x minus 1 thing going on, and there's also a minus 5 at the end. So the x minus 1, what that's going to do is it's going to move the function 1 unit to the right. The minus 5, what that's going to do is it's going to move the function 5 down. So if I go to graph this, instead of starting at 0, move 1 to the right and 5 down. Now I'm going to start down here. But there's no stretch. There's no number in front of x squared. So it's over 1 up 1, over 2 up 4. And our parabola looks like, whoops, let's try that again. The parabola looks like this. We can also stretch the shape of a graph by changing the coefficient in front of the x. Or technically the x squared. So we're going to compare two functions. We're going to compare y equals x squared to y equals 2x squared. All right. Y equals x squared, we can just graph it. We're going to, maybe we'll do that one in blue. So starts at the origin, goes over 1, up 1, over 2, up 4. So this is the original. The table is going to be for y equals 2x squared. Okay. Now, pick the same points. We'll go minus 2, minus 1, 0, 1, and 2. But we've got to now plug minus 2 into our function. So y is going to equal 2 times negative 2 squared, which is 2 times 4, which is 8. The next line will be y equals 2 times minus 1 squared, which is 2 times 1, or 2. Next one will be y equals 2 times 0 squared, which is 0. Next one will be y equals 2 times 1 squared, which is 2. And the last one will be y equals 2 times 2 squared, which is 8. Okay, so we can now graph this over top of the other function, but our points are a little different. Negative 2 has a y value of 8. 1, 2, 3, 4, 5, 6, 7, 8. Minus 1 is 2. 0 is still 0. 1 and 2, and 2 and 8. So I'm going to make these points a little bit more defined. And the function looks like this. So it's a steeper graph, but what I want to focus on is I want to focus on the actual points themselves. If you compare points from y equals 2x squared to y equals x squared, all your y values are double. 8 is 2 times 4. 2 is 2 times 1. 0 is 2 times 0. But essentially, we've got the same graph, except all the y values have been stretched. And that's why we call it a vertical stretch. It's literally like you took the function at the origin, grabbed the function at the top, and you stretched the function out and doubled it in height. That's all a vertical stretch does. So with all this information, we can construct a form of a quadratic equation that allows us to easily manipulate its form, and that's called vertex form. So this is the general form of a quadratic equation in vertex form. It's a little bit different than what we've seen before, but it's very useful for us, all right? And the reason why is our three transformations are built into this function. We've got A, P, and Q, A is going to be our vertical stretch. P is going to be a horizontal translation. And Q is going to be a vertical translation. All right. And now the other thing to think about is all of our graphs had the vertex at the point Q, if it's been shifted left or right for X, and the point P, if it's been shifted up or down for Y. So essentially the vertex is just whatever we've moved it to the right for X and whatever we moved it down or up for Y. And the vertex is P and Q. The vertex equals the point P and Q. So in vertex form, we are given enough information that we can graph the function and find its vertex immediately. And we don't have to guess as to what the function looks like. If instead I gave you something in standard form, if I wrote like y equals 3x squared plus 2x plus 1, you probably have no idea where that function is. I don't know where the vertex is by looking at it. I know it's upright. I know it's going to be a little bit stretched because of the 3. I don't know where the vertex is. This one tells me where it is, and I don't need to do any more work. So we can now work backwards from given information to find the equation of a parabola. So this is where it all kind of ties together. If we're given information on the function, we can build vertex form, and we can solve for anything we don't know. So a parabola has a vertex 6 and minus 5 and goes through the point 2 and minus 9 to find the equation. Okay, well, if we have vertex form, I know P is going to be 6. And I know Q is going to be negative 5. All right, so I can now build my function. I know the function must look like y equals a times x minus 6 squared plus negative 5. I've just gone and placed 6 where p was and minus 5 where q is. Okay, but now I don't know what a is. That's where we need to use this point. And this is kind of a complicated trick, but it is something you need to know how to do. And it is something that you will continue to do even in grade 12 pre-calc as well. We're going to use this point and this equation to solve for something we don't know. What we do know is it passes through this point. This is an x value, and this is a y value. I can take these x values and y values, put them in this equation, and I can solve for a. And that's exactly what I'm going to do. So step 2 is going to be solve for a. I'm taking this equation, but instead of y, I'm going to write negative 9. And instead of x, I'm going to write 2. So it's negative 9 equals a times 2 minus 6 squared minus 5. I can now simplify this by moving everything around. So I'm going to add 5 to both sides. So we'll get minus 4 equals a times minus 4 squared. I can simplify further. Minus 4 equals 16a. And I can divide by 16. So minus 4 over 16 equals a, or negative 1/4 equals a. So now I've solved for my unknown using a point that it passes through. Okay, we're going to now go back and we can write the equation in full form. We can write y equals a, which is minus 1/4, times x minus 6 squared plus, or I guess it's minus 5, so minus 5. This is now the equation of our function, and we can double check it. We can graph this on Desmos if we want. Maybe we should do that. just to make sure it actually has those characteristics. So y was -1/4. I'm just going to go 0.25 times x minus 6 squared minus 5. Okay. So now let's check to see if it has the right characteristics. Does it have a vertex at 6 and minus 5? Well, the vertex is 6 and minus 5. It has to pass through the point 2 and minus 9. So when x is 2, oops, if I can actually get to that point. All right, I think we're close enough that you might be able to, there. When x is 2, y is minus 9. So it checks the boxes. This is the equation of our function. We'll go back, we'll do this one more time because it is kind of a weird idea and it's not something I expect you're going to immediately get. We're going to start by building the equation in vertex form, then we're going to solve for a, then we're going to put it all together. So step 1, we need to look at our vertex. The vertex tells me what P is and what Q is. P is 4 and Q is 5, okay? So I know the function must look like, step 1 is to build it. We'll call it build the skeleton. Function. I know the function has to be y equals a times something. That something is x minus p, so it's going to be x minus 4 squared, and then plus q, so plus 5 at the end. Okay. Now that we've built the skeleton function, we're going to solve for a. So step 2, solve for a. We're going to use the fact that it has a y-intercept of minus 43. And I should probably write that out. That means it's got an x value of 0 because it's the y-intercept. It's got a y value of minus 43. So I can now plug 0 in for x and minus 43 in for y. I'll get minus 43 equals a times 0 minus 4 squared plus 5. I can go ahead and simplify this now. So minus 43 equals a times 16 plus 5. We're going to subtract 5 from both sides. Minus 48 equals 16a. And then we're going to divide by 16. Minus 48 over 16 equals a, which happens to be negative 3. So now we can take a and we can put it all together. So step 3, I guess, will be put it all together. So our function is going to be y equals a, which is minus 3, times x minus p, so x minus 4 squared, plus q, which is plus 5. And we're done. So we've gone through quite a bit today. This is a densely packed set of notes. We started out talking about what the basic transformations are. So we talked about translations up and down, left and right. Then we talked about stretches. We then defined the general version, I shouldn't say this, the vertex form of the quadratic function. And we talked about how the vertex form has 3 specific pieces of info. It tells you the vertical stretch, it tells you the horizontal translation, and the vertical translation. So if I gave you a function in vertex form, it's much easier than dealing with it if it's in standard form. The question is, if I give it the equation to you in standard form, how do you go back to vertex form? And I think some of you might have an idea. We've done this already, except it's been with equations. We're going to have to complete the square. This is a completed square, but that's a topic for another day. So I've got some questions for you. Page 304, 1 through 7. Give those a try. Any questions you've got, please bring those to the chat tomorrow, and we'll spend a little bit of time answering those questions. I'm going to end the video now. Hope everybody has a great rest of the day, and I will see you all tomorrow in our Zoom chat. Bye for now.